This time we're going to discuss about converting from binary number to decimal number. After that, we are going to discuss the following bitwise operators. First, let's have an example. Given 46 base 10, this is a decimal number, and we're going to find what is the equivalent of this decimal number 46 to binary number base 2. So recall in mathematics that decimal numbers are base 10 numbers and the binary number is base 2 numbers. In the binary number system has two binary digits only, and these are 0 and 1. In the decimal number system, it has 10 from the word decimal means 10, and from the word binary, bi means 2. So binary number system has two binary digits, and these two binary digits are 0 and 1, while in the decimal number system, this has 10 decimal digits, and these 10 decimal digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are the 10 decimal digits available in the decimal number system, and these are the two binary digits 0 and 1 available in the binary number system. So we are going to discuss now how to convert from decimal number like this one, 46, base 10. Base 10 means that this number is a decimal number, or it is a number of the decimal number system, and the base 2 here means that this number is in binary number system. In the binary system, these are the bit positions of the binary number system. From the rightmost position, it is 2 to the 0, and going to the left, the next would be 2 to the 1, the next is 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8, and so on. And given these binary bit positions, each binary bit position has a decimal integer value. So 2 to the 0 is 1, right? Anything raised to 0 is 1. 2 to the 1 is 2. This is 2 to the 2. This is 4. And 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. 2 to the 6 is 64. And 2 to the 7 is 128. Say we have here an 8-bit binary number. This is 1, 2, 3, 4, 5, 6, 7, 8. That's 8 bits. The rightmost bit position has a value 1, and next is 2, 4, 8, 16, 32, 64, and 128. Okay, and so on. So when we have a value for this, such as 1, this is 1, 0, 1, 1. This is a binary number, so base 2. What is the equivalent value of this binary number in decimal form, or what is the decimal number equivalent of this binary number? So all you have to do to get the equivalent decimal number of this given binary number is to multiply each bit here with the value in that position. Okay, so 1 times 1, 1 times 2, 0 times 4, 1 times 8. And then you add all, you get the sum of all the products. So that's the decimal number result equivalent of this binary number. So this would now be 8 times 1 is 8, plus 0 times 4, that's 0, plus 1 times 2, that's 2, plus 1 times 1, that's 1. So the sum of that is 8, 9, 10, 11. Okay? So 11 base 10. So 11 base 10 is equal to 1011 in binary. Okay? Say for example, we have another value 11001 base 2. So this given binary number, what is the equivalent in decimal? Base 10. So again, you have to just multiply the bit in that position with the integer value in that position. So 1 times 16 is 16 plus 1 times 8, that's 8, plus 0 times 4, that's 0, plus 0 times 2, that's 0, plus 1 times 1, that's 1. So you add this, the value is what? 25, right? That's base 10. We would say that 11001 base 2 is equal to 25 base 10. So this is the decimal number, 25, and this is the binary number. How about if we have a binary number, which is 1011010. So this is a binary number, so this is base 2. And say we're going to convert this binary number to its equivalent decimal number or to the decimal form. To do that, we're going to multiply each bit with the integer value on that bit position. So 1 times 64, that is 64, and this is 0, and this is 1 times 16 is 16 plus 1 times 8, that's 8, plus 0 times 4, that's 0, plus 1 times 2, that's 2, plus 0 times 1, that is 0. Okay? So now that you have the products, you get the sum of these products. So what is 64 plus 16 plus 8 plus 2? That is simply equal to 90. This is base 10. Therefore, binary number 1011010 is equal to 90 in decimal form. So again, this is binary number, and the equivalent in decimal form or in decimal number system is 90. Okay, so this is decimal number. This is base 2, while this one is base 10. This time we're going to convert the given decimal number 46 base 10 to its equivalent base 2 or binary number. How are we going to do that? This is how you're going to convert from decimal number to binary number. You're going to find the largest value among the bit positions, let's call it X, and X should be the largest among this bit position integer values, and X should be less than or equal to 46. So which among these numbers, bit positions, integer values, which among this is the largest but less than or equal to 46? 128 is not that value which we are trying to find, because 128 is not less than or equal 46. 64 is also not the one because it is not less than or equal to 46. It is 32, right? So 32 is the largest value among these values, which is less than or equal to 46. So we set that to 1. And then we subtract that value 32 from 46. So the remaining value would be 14, right? This is the remaining value. Then we do this again, this step. We find a value X which is the largest among the bit position's integer value, and it should be less than or equal the remaining value 14. So which among these values is the largest but less than or equal 14. It is not 16, right? Because 16 is greater than 14. It is 8, right? So we set 8 to 1. 8 among these values satisfies the condition that it should be the largest value and less than or equal the remaining value 14. So it is 8. And then what we do is we set that to 1 and subtract it from 14. So 14 minus 8 is equal to 6. So this time, the remaining value is 6. And then we do this again. Find that largest value among these bit positions, integer value, which is the largest but less than or equal to the remaining value, which is 6. So what is x? What is the value in here? We call x, which is the largest among these values but less than or equal 6. It is 4, right? So we set 4 to 1. And so this will now be, and we subtract 4 from the remaining value 6. So 6 minus 4, the remaining value is 2. So this time our remaining value is 2. So since we still have a remaining value, we do this again. We find the largest value among this, which is less than or equal to 2. Obviously, it is 2, this one. So we set that to 1 and subtract that integer value from the remaining value. So the remaining value is 2 minus 2. This time, the remaining value is 0. And when the remaining value becomes 0, then that's the end of the process. And we set all of these bit positions which are not 1 to 0. So this one here is 0, this is 0, 0, and 0. So what is now the binary number equivalent of decimal number 46? 46 is the decimal number we are trying to convert to binary, and that binary number is this one. You could simply ignore the prefix zeros. Okay, so we could start from here. So our binary number would now be 101110. That's base 2. So decimal number 46 is equal to this binary number 101110. Okay, so our answer here is, on top is 101110 base 2. That's the binary number equivalent to this decimal number 46. This is base 10, while this one is base 2. So what is the solution again? How do we convert from decimal number to binary number? It is simply to, in each step, we find the largest value among these bit positions, and say we call it x, and that value should be less than or equal the remaining value. At the start, our remaining value is this value 46 that we are trying to convert. So it is 46 minus our x here is 32, this one. So the remaining value is 14. And then we do this step again, and that is to find the largest among these bit positions that is less than or equal the remaining value 14. And among that, it is 8, not 16, because 16 is greater 14. So it is 8. So we set 8 to 1 and subtract that value 8 from the remaining value 14. So the new remaining value is 6. And since the remaining value is not yet 0, so we continue the process of finding the largest value among the remaining bit positions, which is this part here, that is less than or equal to the remaining value 6. And of course, that is 4, right? So we set 4 to 1 and we subtract that value 4 from the remaining value 6. And so our new remaining value this time is 2. And since it's not yet equal to 0, we do this again. That is to find the largest value among the bit positions, and the remaining bit positions now is this one, which is the largest, that is not greater the remaining value. It is 2, right? So we set 2 to 1, that bit position with the integer value 2, we set that to 1, and we subtract that integer value 2 from our remaining value here. So finally, our remaining value is 0, and we stop the process. And then all of those bit positions in here that are not 1, we set them to 0. So this is 0, 0, and 0. And then we extract that as the binary number equivalent to 46. So this is now our answer. The binary number equivalent to decimal number 46. And we could remove or ignore those zeros before the first significant binary digit 1. So all the prefix zeros to the left are ignored, and we could start with the first bit position whose value is 1. So this is now 101110. Again, you can ignore the prefix zeros, those zeros to the left. So the next example we are going to do is to convert the given decimal number 108 to binary number. So let's find out what this decimal number 108 is equivalent to in binary number. So let's find out what is the equivalent binary number of this given decimal number 108. So 108 is base 10, and we're going to find the equivalent binary number in base 2. So again, the solution to that is to find the largest integer value from among these bit positions that is less than or equal to 108. So from among these values, the largest integer value that is less than or equal 108 is 64. So we set this to 1, and then we subtract the value 64 from 108. The remaining value is 44. Next step is to find the largest integer value from among these bit positions that is less than or equal to 44. And that would be 32, right? So this is set to 1, and we subtract 32 from 44. So the new remaining value is 12. And next step is to find again the largest integer value bit position in here that's less than or equal to 12, the remaining value. So obviously it's not 16, and it is 8, right? Because 8 is the largest integer value from among these values, which is less than or equal to 12. So we set that bit position whose integer value is 8 to 1, and subtract that from the remaining value 12. So the new remaining value now is 12 minus 8, it is 4, okay? Next step is to find again the largest integer value bit position from among these bit positions that is less than or equal the remaining value 4, and it is now this one, right? 4. So set it to 1. Subtract that value 4 from the remaining value 4, and the new remaining value now is 0. So once the remaining value becomes 0, we stop the process, and what we have here is now the equivalent binary number, where those bit positions that is not set to 1 are set to 0. So this is 0, and so 128 bit position is 0, and the 16-bit position is 0, and the 2-bit position is 0, and the 1-bit position is 0. So the answer here, binary number equivalent of this decimal number 108. So the answer now here is 11011100, and that's base 2. So since the leftmost binary digit is 0, we can omit that one. So we don't have to put 0 here, okay? Because it is not a significant binary digit. So we can omit that. So decimal number 108 or base 10 is equal to binary number 1101100. Now let's try to verify by converting this binary number to decimal and check if we can get 108. So how do we do that? By multiplying each bit here with the integer value of that bit position and then getting the sum of all the products. So 1 times 64 is 64, plus 1 times 32 is 32, plus 0 times 16 is 0, plus 1 times 8 is 8, plus 1 times 4 is 4, plus 0 times 2 is 0, plus 0 times 1 is 0. So get now the sum of these products. What do we have? 64 plus 32 plus 8 plus 4. That is equal to 108. Okay? So we have verified that this binary number is indeed equivalent to the decimal integer value 108. 108 is base 10, while this is base 2. So this time, let's discuss the bitwise operators available in C programming language. These operators are called bitwise operators because the operands are binary numbers. Now let's start with the first operator. This is called the bitwise AND operator. So this has the same truth table as the logical operator AND. Okay, so let's recall the AND logical operator. So the same, the logical AND operator and the bitwise AND operator have the same truth table. Say these operands x, y are 1, 1, 1, 0, 0, 1, and 0, 0. Say this is x logical AND y and x bitwise AND y. So this has the same value, this column and this column. So whether it's logical operator AND or bitwise operator AND, the result is the same. So true and true is true. So that's 1. True and false is false. False and true is false. False and false, that's false. So for the logical AND, remember, and this one, the bitwise AND, they will only result to true when both operands or all the operands are true. So whenever there is at least one operand that is false, or this, the result is, okay, false. So this is the only way that the logical AND or the bitwise AND would give you a result true. That is when all the operands are true. So say we're going to find 46 and 108. What is the result of this one? Base 10, 46, And then you have a bitwise operator, and this is base 10 108. So since this is bitwise operator, the operands are binary numbers. So this decimal numbers 46 and 108 will be converted to binary values or binary numbers. And then that's the time we perform the bitwise AND operator bit by bit, okay, of these two operands. So say this one here is the binary equivalent of decimal number 46, and this one in this line here is the binary number for 108 base 10. Okay, so from our previous discussion, the binary number equivalent of 46 base 10 or decimal number 46 is this one in here. Okay, so let's copy it here. It is 0. From rightmost bit going to left, it is 0, 1, 1, 1, 0, 1. And all the rest of this, we set that to 0. And for 108, the binary equivalent is that. So from the rightmost bit value, we write here 0, 0, 1, 1, 0, 1, 1. Okay? And we set that to 0. So decimal number 46, which is equivalent to this binary, and then you perform the bitwise AND operator. The second operand is 108 decimal number, which is equivalent to this binary number. So performing now the bitwise AND bit by bit from the rightmost going to the left, it would be what? 0 and 0, it is 0. 1 and 0 is 0. 1 and 1 is 1. 1 and 1 is 1. 0 and 0 is 0. 1 and 1 is 1. 0 and 1 is 0. 0 and 0 is 0. Okay, so this is now the binary number result of 46 base 10 and 108 base 10. So what is the decimal value of this binary number? This would be, this is 1, so it is 32, plus this is 8, plus this is, this bit position has integer value 4, and only 3, right? Only 3 bit positions are having a value 1. And so this is 32 plus 8 plus 4. What is the sum? It's equal to 44 base 10. If we're going to run our program now, our first variable for this bitwise and B1 is decimal 46. And for operand B2 or variable B2, the value is 108. So first operand B1 is 46, second operand B2 is 108. If we are going to perform the bitwise operator on these two operands, B1 and B2, and then the output or the result of this, we display the decimal value of that. So when we run this, compile, run, the output is, okay, look at the output is 44, okay? That is what we got here, 44. The result of performing bitwise and on the two operands 46 and 108. Okay, this time let's perform the bitwise inclusive OR. Now the truth table of this bitwise inclusive OR is the same as the logical OR, okay? Remember, the logical OR is double vertical symbols. This is the logical OR. And the bitwise inclusive OR is just one symbol, the vertical symbol. So this has same truth table. And in the truth table, say these two operands xy are 1, 1, 1, 0, 0, 1, and 0, 0. If we're going to get the inclusive, bitwise inclusive OR, so we say X or Y, that's the same with the X or Y logical OR operator. So this one would result for both X and Y 1. 1 or 1 would result to 1 for this and for that. 1 or 0 would result to 1 also. 0 or 1 would result to 1, and 0 or 0 would result to 0. So recall that for logical operator or for the bitwise inclusive OR, the result is true when at least one operand is true. And the only way it would result to false is when all the operands are false or zeros. Okay, so if there is no at least one operand which is true, then the result is false. So if we're going to find 46 base 10 bitwise inclusive or 108 base 10, okay, let's find out what is the result of this. So again, this one is your decimal number 46, and this one in here is your 108 decimal number. Performing bitwise inclusive or bit by bit, starting from the rightmost bit going to the leftmost bit. Okay, so our operator now here is bitwise inclusive OR. So this would be 0 or 0, that's 0. 1 or 0, that's 1. 1 or 1, that's 1. 1 or 1, that's 1. 0 or 0, that's 0. 1 or 1 is 1. 0 or 1, that's 1. 0 or 0, that's 0. Okay? So all of those bit positions with 1, the result, when performing bitwise inclusive OR, the result is 1. So this is 0, 1, 1, 0, 1, 1, 1, 0. And what is this binary number equivalent in decimal number? What is the decimal number equivalent of that? Let's find out. So converting this binary number to decimal now, it would be, the one here is 64. So we have here 64. This one is 32. So plus 32. This one here is 8. So we say plus 8. And then this one here is 4 plus 4. And then the last one here is 2. So what is 64 plus 32 plus 8 plus 4 plus 2? That is equal to 110 base 10. So this is the decimal number 110 equivalent to this binary number. So if we're going to run the program, and this time let's use the bitwise inclusive OR. Okay. So the first operand is decimal number 46. The second operand is decimal 108. Okay, the one that we have in here. So compile and run. Okay, so the output we have here is 110. That's correct. That is the same result that we got here, 110. So the value here is for 46, decimal number 46 bitwise inclusive OR with a decimal number 108, the answer here is 110 base 10. Okay, so this is not a binary number. This is a decimal number 110. Next, let's discuss the bitwise exclusive OR. This is the symbol for bitwise exclusive OR. What is the truth table of the bitwise exclusive OR? Say, for example, we have these two operands, x, y, and x and y are 1, 1, 1, 0, 0, 1, 0, 0. The bitwise exclusive OR, which is x bitwise exclusive OR y, would result to 1 if the two operands are different. Again, exclusive OR would result to 1 or true if the operands are different. This would result to 0 or false if the operands are the same. So for different operands, it would return true. For same operands, it would return false. So exclusive OR will be true if the operands are different. But if they are the same, then it returns the value false or 0. So it is actually an operator that would check if operands are different. If they are different, then it would become true. So in the truth table, 1 exclusive OR 1 would return 0 because these operands are the same. So it would return 0 if they're the same. 1 or 0. 1 or 0, the two are different. 1 and 0, different, so it would return 1. 0, exclusive OR 1 is different. 0 and 1 are different, so it would give you the result 1. And for the last 0, exclusive OR 0, it would result to 0. Why? Because these two are the same. So same 0, same operands 0, different operands returns or has the result 1. Again, bitwise exclusive OR would result to 1 or true if operands are different. It would result to 0 or false if the operands are the same. So this is the same. So 0, same, 0. And these two lines here have different operands. This is 1, 0, and this is 0, 1. So the operands are different. So the result of the bitwise exclusive OR is true for these two lines. So if we're going to perform the bitwise exclusive OR, 46 exclusive OR, 108. So we do that bit by bit, starting from the rightmost bit position going to the left. So between this 1, 0, exclusive OR 0, it's the same, so the result is 0. 1 exclusive OR 0, it's different, so it is equal to 1. This is the same, so this is 0, same, 0, same, 0. This is 1 exclusive OR 1, the same, so 0 again. And for this column, they are different, so the answer is 1. And finally, the last bit position is 0. So the bitwise exclusive OR for 46 and 108 is 1, 0, 0, 0, 0, 1, 0. And this binary number, if converted to decimal number, that would now be, the bit position 1 here is having integer value 64. So this is 64 plus the second bit position 1 here has an integer value 2. So plus 2, the sum of the products is 66, right? So 66 base 10. This is the binary number, and the equivalent of that in decimal is 66 base 10. Now let's try to check if we will get the same result when we run our program. Say we change this operator now to exclusive OR. Okay, let's compile and run. Okay, so the output here, as you can see, is equal to 66. So our result here is correct, 66.